So thank you all for sticking around, and thanks for organizing, for inviting me. So I apologize for people who already heard this talk, or at least version of this talk before, but I promise you there'll be some new insights into this story, and I have a kind of hint here, story of two superconducting pockets, which I will kind of emphasize towards the end. And this is actually a work that has been going on in our lab already for some years now, and this is just a list of people who were involved. We had actually a collaboration with Andrea for one of these samples, and I'll mention the outcomes of that collaboration as well. And then on the theory front, we had a long list of collaborators, including one of the organizers of this conference. So what we kind of, the topic for today, or at least for this last session before the dinner, is a bilayer graphene coupled to tungsten selenide. And even before our work, there was a lot of evidence that in case, if you have this kind of a structure and you apply out of plane displacement electric field, you will induce spin orbit coupling in this system, which will split the bands. And this is just a kind of one characteristic schematic representing this, where you have holes, and this, if you apply displacement field, in this case, the sign doesn't really matter, but such that you push these holes towards tungsten selenide monolayer, you will have this kind of splitting of the bands triggered by the Ising spin orbit coupling. And if you do the opposite this displacement field, you essentially get just a normal expected band structure of graphene. And this already suggests, and I will come back to it, that other spin orbit couplings like Rajba, are at least not in this picture, and we'll kind of, I'll touch upon it later, how much or not they should be. We know that Rajba is not super big, in part for the reason that if you actually do the experiment with the bilayer graphene, you apply this large displacement field, you investigate this range of dopings and displacement fields, you see some phase diagram encoded in this resistance. And if you compare this phase diagram, this portion, with previous work done in Andrea's lab, where he did not use tungsten selenide, you actually see up to the inversion symmetry that had to be to match the features, everything else is matching. So the doping range here is exactly the same. The displacement field is exactly the same. And even the color map boundaries in resistivity are exactly the same. So that means that if there is a Rajba, it's kind of, somewhere there, but it's kind of, it's hiding it in this case. But on the other hand, if you apply displacement field in the direction that you kind of polarize to tungsten selenide, in addition to somewhat modified phase diagram, you have this large pocket of superconductivity, which was kind of emphasized, and this was kind of subject of work. So superconductivity on this side, you can only get if you apply in-plane magnetic field and things like that, and it has a TC, at least measured in this paper, of 30 millikelvin. Well, today I'm going to show you some data here. The superconductivity can exceed half a Kelvin, or can approach half a Kelvin at least. Okay, so just as a record, here's one example where you see superconducting gap. And moreover, one of the comments here with this, let's say, case where you polarize the holes away from tungsten selenide, you actually you're reproducing some of the kind of non-linearity and some kind of non-trivial features that are also present in the case when you don't have tungsten selenide. So the moral of these couple of slides is that below displacement field less than 0, essentially this behaves as just a bilayer graphene, and which doesn't know anything about tungsten selenide, and above you have this huge superconducting pocket. Okay? So now, if you kind of go one step further, you can, I promised you some kind of a high TCs, or at least higher than in the case of vanilla bilayer graphene. And the idea is that now, more you polarize, you're actually your TC is actually getting increased up to some point. And it seems that in the original work we had a few different samples where we could kind of at least make a claim that the TC is related to spin orbit length, spin orbit strength. Okay. Another important point, which sets this system apart from twisted bilayer graphene system, where you can have some twist angle disorder, is that here you can have a lot of insights into the, let's say, configuration of the Fermi surface by performing Shubnikov-de-Haas. So you can just apply magnetic field, look at the doping density, you fix your displacement field, and then you see some oscillations. And the idea is that you can follow this procedure where essentially what you get is an output of Fourier transform. You can get the configuration of, let's say, characteristic frequencies that tells you what is the fraction of the Fermi surface occupied by different pockets here. So I will actually show more data on this, both for various configurations, and this will be very important. But you can already see from this plot here, which was actually done in this displacement field less than 0, where you expect everything the same as HBN encapsulated sample, that in some regimes you can kind of believe that these lines are easy to interpret. In some of them, much less so, let's say. Okay, and what you end up by staring at these pictures, you kind of end up with kind of assigning them these diagrams where you can say, oh, this is probably, let's say, spin valley polarized phase here, where's that? And so on and so on. Okay, so now you can compare. So these are some. This was a picture for displacement field less than 0, displacement field larger than 0. You actually get this superconductivity, and you can then assign, okay, superconducting in this particular sample. Superconductivity lives in this portion of the phase space which have 2 big pockets and 2 small pockets. Okay. So now we're going to do similar exercise for several samples, but the idea is that now I should mention that it was known fact that if you tune the angle between your bilayer graphene and tungsten selenide, you can actually tune the strength of spin-orbit coupling. And this was kind of elaborated in several theoretical works. And it's easy to kind of understand how this works. You just think about these holes virtually tunneling into tungsten selenide and back. And that will give you, some effective spin-orbit coupling. You have to average over the sample, but these are highly non-commensurate crystals, so you can do this procedure. Okay, so now the main experiment is how do you rotate? It's kind of not super easy to rotate in situ, but you can make a bunch of samples, and each of them can be slightly offset. So you start with the flake where you start with a big flake of graphene or bilayer graphene. You start with a big flake of tungsten selenide. You cut your graphene flake. Then you use your tungsten selenide and pick them all up, and each time you pick them up, you rotate it slightly. So then you get a range of samples with the different angles. Okay. And this is how actually they look. They all have multiple contacts, and now you can measure all kinds of things. One of the things that you can actually connect is you can try to convince yourself that you're actually tuning spin-orbit coupling or Ising spin-orbit coupling. And the way how you do that is you want to go into the regime where these interactions effects are, at least suppressed to some extent. So you do small displacement fields, not very large displacement field, but they have all this symmetry breaking, and then you investigate this range of doping, and you do Fourier analysis, and what you get is that you have like these lines which are characteristic to the size of the pocket. They all, at high densities, they all converge to 1/4, which means you have 4 pockets. But now if you go to a smaller and smaller doping range, they split. So that means one is bigger, one is smaller. And that would naturally correspond to this kind of schematics where, you would have this pocket being big and this pocket being small in one valley and the opposite in the other valley, okay? And by this splitting, by measuring this, you actually have some sense of what you do with your pockets, and you can kind of associate, the strength of spin-orbit coupling in this way. So there's an alternative way to do this by crossing of the Landau levels in fields, and we did all the cross-checks that we could, and they are producing consistent results, okay? So at least we can confirm this picture that roughly with 0 degrees, the spin-orbit coupling is the largest. Here is the smallest. So now, if you take all these devices and you just map out the phase diagram, what you get is that higher spin-orbit coupling, higher Ising spin-orbit coupling, your superconducting pocket actually moves to higher and higher displacement fields. And you can summarize this with this essentially graph where you have strength of spin-orbit coupling on the x-axis and displacement, onset of displacement field, like tip of this superconducting pocket on the y-axis, and you can see how this actually goes. So now I can give you the examples. So here are the 2 examples. Now, this is the smallest spin-orbit coupling with 0.4. I think this is the largest. I think it's 1.6 MeVs. And just if I give you a few examples of how the TC evolves with doping. So if you have small Ising of this 0.4 MeVs, you actually, here the pockets, they actually emerge fairly quickly. So at 0.4 volts per nanometer, you already have superconductivity. But the main point is that the superconductivity saturates and the TC is essentially stuck to this, like maybe 150 millikelvin, okay? If you do the same experiment for the large spin-orbit coupling case, you actually have to crank up displacement field much higher. But as a consequence, you are actually getting TC that is much higher by essentially factor of 3 or more. And now you can do this, you can summarize this for all the devices in this kind of a 3D plot, where now you have displacement, you have strength of spin-orbit coupling, and you have optimal TC. So optimal TC both in displacement and the density. And then you can see the behavior of all of these devices. So essentially, if you have a low spin-orbit coupling, your graph looks like this. So it's essentially kind of onset very early, but then it's kind of saturated in TC. And the other ones, kind of onset much later, but they also reach higher spin-orbit coupling. All right? So that's kind of that was some knowledge that we knew already for some time, but now we wanted to kind of investigate more details, what's going on with some of these samples, and for the rest of the talk, I will focus on the samples that have kind of large spin-orbit coupling, okay? As opposed, so essentially some kind of samples like this, as opposed to this one, okay? Yeah?
Sign of displacement field where you get this, should I think of it as electrons going up against the...
Yeah, holes, yes.
If the holes
Holes.
Up against tungsten.
Yes, all of this is for holes going up against tungsten selenide, okay? So the reason why I'm saying we are kind of focusing on this case is because, I mean, here it's maybe not super obvious, but the idea is that instead of having just one pocket of superconductivity, which we have for this small Ising, we actually have multiple superconducting pockets in case of large Ising. And in total, we actually found 3 superconducting pockets. So these are this SC1, SC2, and SC3. So SC, everything I told you so far is the SC2 here. That's the biggest dominant, most dominant pocket. So SC1 was actually discovered here at UCSB by us sending samples to Andrea, where he kind of figured out that in one of the samples that he can measure this SC1. And then SC3 is just kind of discovered by us systematically searching for this effects. And if you think about these SC1, SC2s, here are some line cuts. So this one is taken at this displacement field, and these two are taken in these 2 displacement fields. And now you can ask, okay, how similar or dissimilar these superconducting pockets are.
Good question.
Yes.
What are the Fermi surfaces? Do they have the same Fermiology, these 3 pockets?
No, and I will, yeah, and this is something I want to discuss, that exactly that they have very different Fermiology. But before we kind of dive into Fermiology, they also have a very different in-plane magnetic field dependence. And that's kind of important. So if you think about in-plane dependence, you can define something called Pauli limit violation, magnetic field, Pauli limit magnetic field, which is actually just a multiplier of TC. So essentially, the higher TC, the higher this field is. And essentially, if you have Ising spin-orbit coupling, you do expect Pauli limit violation ratio, high Pauli limit violation ratio. And if you think about all of these superconducting pockets, they actually saturated different, they actually get extinguished by the field at different magnetic fields, which are all over the place. So essentially, this, actually these smallest, the pockets that have small TC, they have very large Pauli limit violation ratio. And the one that is essentially the biggest TC has this weird Pauli limit violation ratio where, on one end, this Pauli limit violation ratio, I think it kind of saturates around 2, 3, but on the other end, it can be all the way up to 10, okay? So there is something funny happening with these pockets, even if you focus on one pocket itself. So now we can kind of think of what actually determines this Pauli limit violation ratio. So if you actually very naively assume that everything is dominated by Ising spin-orbit coupling, then this Ising spin-orbit coupling gives you some energy range. I mean, it's like 1.5 MeVs. If you want to convert that to some magnetic field, you are getting like something around 20 Tesla. So clearly something is helping or something is different in these pockets that kind of actually preventing reaching to 20 Tesla, okay? So one possible thing that is worked out with the theorists is that if in the presence of both Ising and Rajba, you would have this suppression of superconductivity, but we don't really see evidence of strong Rajba in this system. Another thing that is considered seriously is this orbital depairing. So orbital depairing, you just apply a magnetic field in plane, and because these wave functions live on both top and bottom layer, you could think that there is some depairing happening because there's a flux penetrating through this, basically essentially through this kind of delocalized wave function. But these displacement fields are large, so the question is how much you can explain away with the orbital depairing, okay? And, you know, is there other mechanisms that could play a role? That's something to kind of just keep it in your mind. So first I will very briefly mention this SC1. So the SC1 is, again, is just a reminder, this superconducting pocket here. So if you actually do this experiment trying to figure out the Fermiology where this SC1 happens, it happens close to this transition where you have essentially two big pockets, three small pockets, and two big pockets and two small pockets, okay? So it's definitely on this side. And I'm not going to talk too much about it, mostly because I was thinking that maybe Andrea will mention it, but he decided to talk something else. But the idea is that in this particular case, because you have this kind of situation which is nominally maybe not nematic, you can try to model it, and at least to my understanding, there are some results from Weizmann that suggest that you can explain this away, or at least the power limit violation ratio here, with just orbital depairing, okay? You don't need to invoke Rajba, at least. But the idea is that, so the reason why I'm kind of starting with this one is because this one is thought to be the simplest one, because you have, you know, two big pockets and three small pockets, so the nematicity, for example, which is present here, maybe does not affect any of the explanations, okay? So now, let's see what's happening in these two other pockets. So now we are essentially in displacement field, which is here, and we have two superconducting pockets, the big one, which I showed you, and then this small one here. And essentially, if you look at these evolution of the frequencies, you can clearly identify that there is some transition happening here because this line disappears. That's the end of this. But the superconducting, and then the other end is here, where exactly you kind of lose the superconducting pocket. So similarly as SC1, this SC3 lives in this region here, but very close to the boundary, with where you kind of have this kind of rearrangement of the pocket. Okay? So now the challenge here is that if you look at all these lines, the assignment of the Fermi pockets is not super straightforward. Also, what I kind of, I'll show you the Fermiology in a moment, but again, as just a reminder, so this superconducting pocket here actually survives all the way up to 7 Tesla, while this kind of pocket here, which is very symmetric in critical temperature, becomes very asymmetric with the in-plane magnetic field. So I'm just going to kind of give you results, and maybe we can discuss how did we get these results. But essentially, if you map these lines, so what you can do is you can actually map the lines at various displacement fields and various dopings, and you can take different ranges of magnetic field which you use in the Fourier transform to identify the main lines, okay? So some of these lines are real, some of these lines are just harmonics, okay? And it turns out that in this particular region, you actually have one big pocket, then 3 of some medium-sized pockets, and then one very small pocket. So we have additional evidence that this is most likely some sort of an intervally coherent state. But at least intervally coherent state can explain, or it give you some give you some explanation why this magnetic field in-plane magnetic field is so large, even though the TC is much weaker here. Of course, this arrangement is just completely artistic. Yeah.
Can you quickly connect this range to that picture on the left? Where exactly this orbit surfaces are?
It's the same. Oh, so it's essentially okay. So the whole region here is this whole range, but you get superconductivity only in this small section. So the superconducting pocket, so this weird phase, 131, is everywhere, but you get superconductivity only close to the boundary of that phase. Okay? Then, so essentially, if you go from this way to this way, you enter the phase, this 131, you enter the superconducting, then you kill superconductivity with doping, and then you're still there, and then when there is another transition, you kind of emerge on the other superconducting phase. Yes?
So the insulating phase on the right-hand side of the superconductor is going to be what kind of order?
Let me go, if I can quickly pick it up. So it's not insulating phase, it's a metallic phase. Let me see if I have it on the previous slide. If not, I have to come back to you with this. Let me come back on that, because too much here. Okay, so this is 131. So now the question is, of course, what's happening with this phase, and in particular, at least, these asymmetry should be kind of seen somewhere in this Fermiology. Or at least there might be some other explanation. Okay. So now, actually, if you look at far away, so this portion of the phase here, and far away into the normal state, it's actually relatively simple to kind of convince yourself that this is 2-4 phase, which is exactly the same as we found in the previous samples with large spin orbit coupling. So essentially you have so in contrast to small spin orbit coupling sample, where you have 2 big, 2 small surfaces, now you have 2 big and 4 small surfaces, okay? And we are just assuming that this is like, that there's no intervallic coherence, but the idea is that, you have some kind of spin valley arrangement like this, okay? The thing is that if you are careful enough, which were not in the original experiment, you are very tempted to say that the whole thing is just one phase, which I just assigned. But if you look closely into this particular region, you actually see that there is some other structure emerging. So essentially, you kind of go down here, meaning that these 4 pockets get smaller, but then there is some transition here, which is actually right in the middle of this superconducting transition. So it's kind of not very obvious why it happens. And then this line kind of stays the flat. And if you have a willing eye, you might actually see another line connecting from here. It's very vague, so you have to actually zoom in to kind of hunt for this line. But the idea is that once when this kind of saturates, you actually, so the cross checks for all this is you actually sum up these frequencies and you have to get 1 as an answer. So that you kind of account for the whole Fermi surface. And you are stopped doing that beyond this point, essentially, because this line, if you would want to kind of account for that, you would have to go down, and it doesn't go down, okay? And I'm running a little bit out of time, so I'm just going to show you the solution. The solution was that in contrast to this FP22 phase, or 2-4 phase, sorry about this, here we now have 2-2-2 phase where these small pockets are starting. So one of these small pockets starts to shrink, and it actually shrinks down to almost 0 when you hit this phase boundary. And funny enough, this is actually where, you know, you have this strong deviation from the Pauli limit relationship, this kind of crookedness of the phase diagram. And the way how we actually kind of explore this is that, you know, within this region, you can actually do a different experiment. You can plot your TC as a function of the in-plane magnetic field, and you can kind of try to fit these curves with, you know, some kind of a second-order polynomial. And the idea is that once, when you are kind of in this regime of 2, 4, you actually, everything fits relatively nicely with this TC is TC0 magnetic field minus some kind of a second quadratic term. In this quadratic term, the prefect of this quadratic term is essentially constant, more or less, while you're in this phase, okay? We did actually a cross-check experiments where you kind of go sufficiently low in displacement field, where the whole phase becomes just this, superconducting phase, and you actually have only constant phase here. But then on this other end, where you have this kind of weird elongation, you know, you just use a small portion to kind of fit this alpha. You see that this alpha is kind of linearly dropping off as you get into essentially as this pocket gets smaller and smaller. Okay. I will kind of stop here and formulate this as a puzzle, since this is a theory conference. So you can kind of figure out your favorite solution to this. But I just want to kind of use one last slide to summarize. So essentially, the beauty of this system is this is like an ultra clean superconducting with a, you know, manageable TC, where you can actually work and get decently high quality data. We found these, you know, strange superconducting pockets where, in one case, you have some Pauli limit violation, which is probably related to the IVC state. And then in these other pockets where things are more complicated, you can actually provide some insights if you are, you know, willing to measure, willing to kind of put time and effort and students into doing very careful measurements. And the hope is that, you know, because these detailed measurements are indeed possible and not maybe limited by some kind of level of impurities and disorder, maybe we can kind of resolve which details are more important to achieving higher TCs and which ones are irrelevant. So I'm happy to take some questions. Thank you for sticking around.
Questions? Just a second.
Okay, thanks. So I was curious about the 131 states. I mean, you label them purple, but I can hardly imagine the two values are completely compensated, right? So do you have an anomalous Hall above TC?
No, but if it's intervallic coherent state, so the idea is that it's an intervallic coherent state, not spin value polarized state.
I see, that's why it's purple.
Yes, that's why it's purple. Sorry. Yes.
And is there anything abnormal in response to the vertical magnetic field, autoplane magnetic field?
You mean in terms of superconductivity?
Yeah.
Or? Well, the critical fields in out of plane are relatively small, of like tens of few or at least 10 or most 10 millitesla.
Okay, thanks.
Yeah.
Is the maximum in TC correlated with the start of the change of this pocket when it starts to shrink?
No. You can see that for example, it's close. Okay, let me put it that it's close, but at the moment we don't believe it's exactly the same point.
It's a bit larger density where the pocket starts to shrink than the optimal TC?
So the point here, I think this is something that I cannot answer with certainty, in a sense that the maximum, you know, so this transition we kind of label it, let's say this is maybe 8.3, and here is maybe 8. So within the error bar, you can assume that it's the same, but the it's really because this range is a little bit, elongated. So I would say I would say that I cannot provide yes or not at this particular moment in time. Meaning making a claim that these two are exactly the same point is a big claim. That's where I'm going with.
I have a very simple question. You have this wonderful detailed information about the sizes and form of the pockets. Do you have any information about the values of the Fermi energies?
Values of the Fermi energies.
Right, to compare with TC. You have a pocket.
Yes.
Right.
Well, okay, so the question is which pocket?
Take the largest one.
The largest
For
pocket.
example, take the largest one, just to give a scale to compare with critical temperature.
Well, I would have to come up with a number on the spot, and maybe I can come to that offline. That's because it's like I'm pretty sure you can work it out. It's just that we didn't work it out, so I don't have a number in my head.
It would be good to know whether Fermi energy for all these pockets is larger than your largest TC or comparable.
Okay, yeah. We'll come back to that. Yeah, thanks for that. It's a good suggestion.
Yeah, I just want to confirm a couple of things you said. So the puzzle you mentioned is that if I look at the trend for alpha, that the coefficient of B squared, you would think that the superconductor on the right, the right half of SC2 would have a larger field. It responds less to the magnetic field. So you'd think that it would have a larger critical field. But in fact, it has a smaller critical field. Was that the puzzle you were mentioning?
No, I'm not sure if I understood your question.
Yeah.
So essentially, you have this alpha. So left from this transition, when these kind of pockets stay the same, it's roughly constant. So essentially, I don't even know how to think properly about this alpha, in a sense. Except that I can make a claim, experimental claim, that it appears that it's connected through the, let's say, difference in sizes of these small pockets.
But the field I need to kill the superconductor on the left half, was that bigger?
No, it's smaller.
It's smaller, okay, so it's consistent with this value
Yes,
of alpha
yes,
being
yes,
large.
yes.
And the other thing is all the superconductors you see have one end of them connected to a Fermi surface changing transition, is that right?
Let me confirm. I tend to say yes. So definitely these two, and also the first one as well. Yes. So, although sometimes this change is a little bit fuzzy, more fuzzier than when there's a rise in TC. But it's
close at least.
It's close. It's close enough. Yes. So this is to kind of is there any fluctuations that can be here? I guess the argument against that, which I am pretty agnostic, is that some of these phases are pretty large in the density, and then you have to work out, whether fluctuations can survive within this deep in the pocket. Yeah.
So you mentioned if you move to the sample with larger spin-orbit coupling, you actually need larger displacement field to stabilize the superconductivity.
Yes.
Is it counterintuitive? Do you have a reason why that's the case?
I don't have a super intuitive reason why this happens. Mm-hmm. Some of our theory collaborators think that they have theory that explains it, but it's still not super intuitive. But the idea would be that at least utilizing some of these models, if you think that the density of states is the important driving factor, then you have to take into account that you have two effects can happen. You either raise the density of states and you get into the superconductivity, or you raise the density of states and then you trigger some phase transition, like a Stoner criteria. And for the reasons that are not completely clear to me, or at least I cannot articulate them well. If you increase spin-orbit coupling, you would kind of favor superconductivity or disfavor the Stoner criteria. And in that framework, you can actually obtain that larger spin-orbit coupling will give you larger displacement field. This is how much I can comment, sorry about that.
Hi, thanks for the talk. I have a clarifying question. So you're drawing this phase changes of Fermiology on the D direction. Did you see anything interesting on vertical direction? Because I think let's say the SE3 and SE2, the Fermiology are different, as a matter of fact.
So, sorry, SE2 and SE3?
I mean, if you go vertical direction, I'm just saying there could be also like phase changes in your Fermiology, right?
Yeah. It's.
Well, I'm not particular about that superconductor, just like maybe let's say in the region of superconducting 2, is there similar transition as you show in this direction as in the other direction?
Well, you would get the same transition like okay, we didn't map up the boundary, where is the, where is this green boundary? As a function of displacement field, but I'm pretty sure that it has some, it has some boundary. So you would get the same transition probably with the displacement field.
I see. So there's only one transition over all? Right.
Okay, there's at least one.
Okay, thank you.
Yeah.
Any other questions?
And what happens with the area of the big pocket as you cut through this dome? Is it just staying roughly the same?
It stays roughly the same. It stays roughly the same. So essentially, here's the kind of the data. You just have essentially this thing. This is the.
It's kind of growing, but not too much.
Yeah, it's relatively growing if you go to the, if you go to lower hole doping, it's growing. But the main point is that a lot of things is absorbed by this smaller pocket, because the smaller pocket, this small pocket doesn't shrink anymore, or relatively, yeah. So I mean, you can kind of theorize why this could happen with some in-plane field and things like that. Yeah.
Any other questions before we go to our reception? If not, let's thank our program.